so we're going to jump right into talking about the product and quotient rule. So you might remember, like actually, let's go back here. When we did these derivatives of polynomials, like basically learning the big rule was the power rule, but also, we could pull out a constant multiple, right? If I was multiplying by a constant, that's so we just bring that constant down, right? And then use the power rule on the rest. And then also we had this rule that said, we could split up, like if I'm adding or subtracting stuff that I'm taking the derivative of, just split it up. Just take the derivative of each, right? Differentiate each and add or subtract them. Super convenient. Now, if what I'm doing is multiplying two functions, like if I have a product and both factors have an x, right, have a variable, it's not just a constant, we cannot split up a derivative over a product or a quotient. And so we have this handy product rule here. We're going to talk about the product rule first, and then we'll talk about the quotient rule. Basically, the way the product rule goes is, suppose I'm multiplying two things that I could view as functions in their own right? They both have x's. Then to get that derivative, what I'm going to do is just take turns. I'm adding two products together, right? And then I'm just taking turns. Which function am I taking the derivative of? And which one am I just grabbing that function straight up? Right? So I've got g times f prime plus f times g prime, and I add them together. I'm going to first convince you or show you why this product rule is true. You don't necessarily have to write this down. I'm sure there's a demonstration of it in the textbook. But if I want to find the derivative with respect to x of f of x times g of x, well, let's take what we know a derivative is. It's the limit, as h approaches 0, of, and in this case our function is that product. So that the way this looks when we set it up is I have f of x plus h, g of x plus h, minus f of x, g of x, all over h. Right? That's what I want to be able to do, is evaluate this limit. So in order to derive that product rule, we're going to use one of the most time-honored tricks in all of mathematics. I'm just going to cleverly choose an expression to add and subtract. I can add and subtract the same thing, right? It's just adding 0. So here's what I'm going to add and subtract. So I've got my f of x plus h, g of x plus h. And I'm going to do it right here in the middle because it's convenient for me. So let's see. I'm going to subtract f of x plus h, g of x, and then add f of x plus h, g of x. Right, so those expressions are equal, right? Because these guys sum to 0. Now what I'm going to do is just use an algebra fact. I can split up a fraction over addition and subtraction that happens in the numerator. So I can write this fraction I'm going to split it up right here. So I've got f of x plus h, g of x plus h, minus f of x plus h, g of x. Plus, now when I split up that fraction, I'm actually just going to split up the limit as well. We could split up limits over addition and subtraction. So I've got the limit as h approaches 0, and then what I've got here in the second fraction is f of x plus h, g of x, minus f of x, g of x. I'm going to stop there for a moment and see if we're okay right here. There's questions on how we got to this one. You look dubious. Yes.
So it's the first and the last. So f of x plus h, and then you're subtracting and adding g just of x, not of x plus h.
Yeah. So I'm the thing I'm subtracting and adding is f of x plus h, g of x, which I'm allowed to do. I could add and subtract, I don't know, f of x plus 2 g of 3 if I wanted to, right? But that's not going to be helpful. So I'm being like, this is like, you know, we can add and subtract the same thing. The idea is like, we want to do it, we want to be clever about what we pick. As it turns out, this is a really clever choice to make. So, so now what I'm going to do is rewrite. Just notice, look what we have here. I've got a common factor of f of x plus h, so I'm going to take that out. And then here, I've got a common factor of g of x. So I've got the limit as h approaches 0, f of x plus h, times, and then this fraction, g of x plus h minus g of x, all over h. That's the first limit. And in the second limit, I could take out a g of x, and then what's left inside in the numerator. Now, right about now, things might look a little familiar. We can split up a product. We can split up a limit over products. So this first limit I could write as the limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x all over h. And I'm going to do the same thing with the other limit. So plus the limit as h approaches 0 of g of x times the limit as h approaches 0 f of x plus h minus f of x all over h. Now we're pretty much done, right? Let's let h go to 0. If h goes to 0, what does that limit approach?
Doesn't just approach f of x?
Yeah, right? I mean, I have f of x plus h. If I let h shrink to 0, that's definitely approaching f of x. And what about this limit right here? Do we have a name for that? Yeah. Plus, I'll go over here. If I let h go to 0, what does g of x get close to? It's kind of it's going to feel like a trick. It's not a trick question. Like, g of x, right? That g of x doesn't depend on h at all, right? G of x is just g of x. And what about this limit here? F prime of x, right? That's the derivative of f. That's the limit definition. So here's our product rule. I've written the sum. Here we've derived it with the sum written in a different order, but of course addition is commutative, so it's the same thing as presented in the notes. So this is why the product rule is true. I'm not going to ask you to recreate that process, but I wanted to convince you, and hopefully I have. Is there a question?
No, I was just right.
Oh, okay. Yep. So what we're going to do next is just get some practice using the product rule, and then we'll look at the quotient rule. We won't prove the quotient rule, but that's also in the text somewhere. It's a similar process where you add and subtract the same thing and kind of split up the limit. All right, so here's how this works. When I am using the product rule, I often do a little bit of side work. So I've identified I've got two factors I'm multiplying. They both have x's. The first step in applying the product rule is recognizing when you need to use the product rule. So since both of these factors have an x, we're using the product rule. We also have the option to just multiply that out, right? Like we can do algebra, but we're going to get some practice using the product rule. So I'll let this be my f function, and maybe this will be my g function. So I'm going to go over here. F is x squared plus 3. And so what is f prime? What is it? Nope. Yeah, right, the power rule. And the derivative of 3 is 0. And so g is 3 minus 2x. So what is g prime? What kind of function is 3 minus 2x? Like conceptually, I mean, we could do this using rules, and you will, but like as a concept, I think we can also figure out what this derivative is. It's not 1. What'd you say? It's a straight line. Yeah. So when we think of the derivative as a slope of a tangent line, if your function is linear, the derivative is just its slope. It's -2. So the derivative of a constant times x is just the constant. You can also get that from the power rule, right? That's 2x to the first. You bring down the 1, and then you have -2 times x to the 0, and x to the 0 is equal to 1. All right, so now let's set ourselves up. H prime of x. I'm going to just write the product rule first. G f prime plus f g prime. I'm going to write it down fresh every time because I know this is a rule I'm going to need to know. I'm going to be expected to have it memorized and probably need to use it on the quiz next week. So now I'm just plugging stuff in from what we filled out before. So gf prime is 3 minus 2x times 2x plus fg prime is x squared plus 3 times -2. Now I'm going to multiply and combine, just simplify this expression. This is the first part. We always want to simplify our results. So we're going to distribute that 2x, and then distribute the -2, and then combine like terms. You could leave it like that, or you could factor out maybe a -6. Some people like to do that. Either is fine. How we doing? Aaron's like, you know what? I'm Should we try another one? Good. Let's do it. All right, so the first step in applying the product rule is recognizing when you're looking at a product, and you need to use the product rule. So our f function, it doesn't matter which one you call f or g, right? Because multiplication is commutative, but I usually just go in order. So let's say f is 3 minus x minus 2x squared. What is f prime? That is part of it. Yeah. Right, because the derivative of -x is -1. Our g function is x to the 4th minus 4. So what is g prime? It's like a little game. Keep guessing. You could do it. Close. 4x to the 3rd. Right? So we're practicing this rule right here that says the derivative with respect to x of x to the n is, we bring that power down in front, n times, and then we just reduce the power by 1.
You drop all the other constants out of variable.
Yeah, because the derivative of a constant is 0, right? That's another rule that we're using. A derivative describes how a function changes, so a constant function doesn't change at all. Its rate of change is 0. All right, so now I'm writing down the rule again. G times F prime plus F times G prime. And then we just plug stuff in. So G times F prime, that's x to the fourth minus 4 times F prime is negative 1 minus 4x plus F G prime, 3 minus x minus 2x squared, 2 prime 4x cubed. This is the start. What we have here is certainly equal to the derivative, but we always need to make sure we're simplifying our results. So let's multiply this out and combine like terms and see what we get. So the first one we're going to FOIL. Let's see. X to the fourth. So we have minus x to the fourth, positive 4, minus 4x to the fifth, positive 16x. No like terms there, so I'm just going to throw these in. I'm going to probably just throw them in a descending order of power of x's. So negative 4x to the fifth, minus x to the fourth, plus 16x, plus 4. And the next one is just one term to distribute through, so we have a 12x cubed minus 4x to the fourth minus 8x to the fifth. And we have some like terms, I guess, right? There's our x to the fifth. So we have a negative 12x to the fifth. We have our x to the fourth powers, negative 5x to the fourth. And then I think those are all the like terms. So plus 12x cubed, plus 16x, plus 4. Now, the rule as I've written it in the notes, and the way I always write it out, like obviously because you're adding, it doesn't matter what order you put that product in, but I always write it with the G F prime term first. And the reason that I always do that is because if you look at the quotient rule on the next page, and I'm going to just, does anybody need me to stay here for a moment? So if you look at the quotient rule is very similar. Like it involves the same products, right? GF prime and FG prime. We're dividing it by g squared in the bottom, but we're subtracting up here. So subtraction is not commutative, so it actually matters. So the reason I always write GF prime first, even with the product rules, because I'm just in that habit, and then I know I'm not gonna mess it up here. If you did mess it up, you'd just be off by a sign, right? When you reverse the order of subtraction of something, it just changes its sign. So we start the same way, and when I say start the same way, I really mean the first step in using the quotient rule is understanding that you need to use the quotient rule, like recognizing when you're looking at a quotient. What makes us have to use a quotient rule here is that not just that we're dividing, but there's x's in the top and the bottom. So we go about it basically the same way. Here, division, not commutative, it absolutely does matter. F has to be the one on top, G has to be the one on the bottom. So, do a little side work. 3 minus 2x for F. What is F prime? Negative 2. And our G is the bottom function, x squared plus 2. What is G prime? 2x. Good. Look, we haven't needed to do any limits, right? How nice is that? All right, so Q prime of x is G F prime minus F G prime all over G squared. And we have the pieces we need, so we're just going to plug them in. gf prime, that's x squared plus 2 times negative 2. And then I'm subtracting 3 minus 2x, there's our f, times g prime, which is 2x. This is all over the square of the denominator. We've got some simplifying to do, of course. This is definitely not simplified. And, as always, we are resisting any urge that we might have to cancel over addition, right? Do not let yourself even consider the possibility of doing that. And that should be squared.
Yeah.
Yep. So that should be squared. But also, yeah, can't, right, we're subtracting. Don't cancel over addition or subtraction. What we're going to do is just multiply out the stuff in the top. Find those products and then simplify. Oh, I said multiplied out and then I didn't. Okay, let's try that again. So we have negative 2x squared minus 4. I'm going to distribute this 2x and at the same time distribute that negative. So we'll have a negative 6x plus 4x squared. Now we're multiplying out the top because we have, it's a sum of products, right? The top, we'll just understand that this, what's in the numerator, is not factored. I have some products, but then we're adding them together. So like, it's not like we've written a numerator here to begin with, like just as a product of things. If we had, often like expressing something in a factored form is desirable, right? But it is not factored form. That's why we have to multiply it out. Contrast that, oh, I dropped the square again. Contrast that with this x plus 2 squared here. If you like just really want to, you could multiply it out, but it gets you nothing, right? And in fact, can be really inconvenient if you're trying to use the derivative to like analyze your function. So just leave this factored. Leave that as g squared in the bottom. We're going to combine like terms, so we've got 2x squared minus 6x minus 4 and then we could take out a 2. I guess you could leave it that way. If we take out a 2, it looks like this. Oh, minus 2. And then when I have something that's a fraction, sometimes even if it isn't a fraction, I always try to see like, oh, well, that factor, like, could I unfoil that? And I'm pretty sure that's irreducible, so I think I'll leave it as it is. So there's our q prime of x. How's that? Let's do another one. And so here's it's like an application, I guess, or at least they've given us some context to this problem. They tell us that the concentration of some drug in the bloodstream is modeled by that equation, that function, where t is the time in hours after the drug is taken, and we want dc dt. So before we even think about setting up the quotient rule or anything, it might be helpful to think, what do we expect to happen? Maybe take a look at the graph too. But if I look at the behavior, like if you imagine, like, so just the drug, like initially at time 0, the drug is not your bloodstream at all, right? So it starts out at 0. Then you take the drug and the concentration rises. And it'll rise until it like probably peaks at some point, and then your body's working to eliminate it, so then it kind of is going to level off. So we'll probably see that kind of behavior in the graph. And I'll just start it at 0. I don't know what the, let's say I'll go out like 10 hours or something, And I don't really know. Let's see, at 0, I'll just have y go up to 10 as well. Let's take a look at that. All right, so maybe I'll let x go out to 20. So something like that. So here's the behavior, kind of what we might expect to have happen. Now let's find the derivative. We'll go through this process, find the derivative, and maybe we can kind of compare the behavior of those two functions. So we want dc dt. The first step in using the quotient rule is recognizing when you need to use the quotient rule. So we're dividing two things. They both have our variable t in them. So our f function on top is 25t. What is f prime? 25. And our g function is t squared plus 5. What is g prime? Two t. So dc dt is, I'm going to write down the rule again because I got to memorize this, g times f prime minus f times g prime all over g squared. So g times f prime, t squared plus 5 times 25 minus fg prime, that's 25t times 2t. This is all over the square of the denominator. We are, of course, never going to cancel over addition. Ever. Don't do it. So what do I need to do? Yeah, we need to multiply out these products, see what we can do to simplify the top. Plus, that's 125. Minus, that's 50t squared. And so we've got negative 25t squared plus 125 all over t squared plus 5 squared. Well, let's take out a just for fun, because I find it convenient, I'm going to take out a negative 25 from the top. And if I take out a negative 25, then we're left with t squared minus 5. And boy, doesn't it feel like, so close, and I wish I could cancel, but they definitely, there's no common factors. So there's dc dt. Now, I'm going to go back, if we're done, if it's okay, we're just going to bring up the graph again. If I look at, this is the concentration, right? This is the original function. And it starts out increasing. So like if I analyze the behavior of the derivative function, right, dc dt, we would expect here, dc dt is going to be positive, right? What's happening there at the derivative? Yeah, it's going to be 0, right? Because it's going to level up, right? So if I imagine like drawing all these tangent lines, positive slope, positive slope, positive slope, 0 slope, and then it decreases. So what would I expect? What kinds of values for dc dt would I expect in this range of values? Negative, yeah, because it's increasing, it levels off, and it's decreasing. So we're going to expect that derivative to start out positive, cross the x-axis, where it's 0, and then dip below because it's going to take on those negative values. I'm going to go ahead and put in that function, and I'll have to adjust the window to allow for negative y values. So maybe I'll go down to negative 10. Oh no, wait, hold on. It's fine, but I I don't want them both to be red. And I don't think I need to go quite that low, so let's try -2. There we go. All right, so the original function's in red. Here's its derivative. It starts out positive. The derivative itself is decreasing, but it's all positive here. And then you could just draw a straight line down, like this place where the blue graph crosses the x-axis corresponds exactly to where that function meets its peak. And then it dips below because this thing is decreasing. What's interesting about this is the function, the original function is increasing, but the rate at which it's increasing kind of decreases itself, right? It starts out increasing quickly, like you just took the drug, your body's like absorbing it. And so it's increasing quite a bit, and then the rate at which it increases, it's sort of reaching its peak, and then your body is working to eliminate it, and so, there's those negative values. As it turns out, the rate at which your body eliminates most drugs is sort of proportional to how much of the drug there is in the bloodstream. So the less of the drug there is, you'll notice the derivative itself is increasing. So that means it's still negative, right? It's still like the amount is decreasing, but just not quite as fast, right? That's sort of what we're observing here in the graph.